Let's discuss unique factorization domains or UFDs. Before watching this video, you should thoroughly review homework 0 for integers and the fact that all of it stays valid for fx where f is a field. You proved unique factorization for these rings, but so far we always regarded long division as the more basic idea. However, unique factorization is much more general. So today we will study it abstractly in arbitrary domains without reference to long division. We'll define UFDs. We will see a characterization of them. We will see that GCDs exist in any UFD, but a GCD may not be a linear combination. And every PID is a UFD, but the converse is very false. There are lots of important UFDs that are not PIDs, and we will see some of them later. In all the reasoning that we will do today, little will be new. The only new part will be about ensuring existence of factorization. And this will require some finiteness condition. Over integers, we had absolute value. For polynomials, we had degree. In general, we will need a more abstract device. So let's start the development. We'll talk about factoring only in integral domains, and we will consider only non-zero elements. So I can always cancel common factors. Units don't count as proper factors. For example, 1 and minus 1 in integers. If two elements can be obtained from one another by multiplying by a unit, then I call them associates. You can check that this is an equivalence relation. For the sake of factoring, associates are considered equivalent. For example, 10 and minus 10 in integers. Here I have written standard definitions of what it means to be a factor and what it means to be a proper factor. A is called a proper factor of B if it is neither a unit nor an associate of B. These definitions can be nicely expressed in terms of principal ideals. We have already seen this one. So take a moment to work through the first 4 lines. Before I define unique factorization, I have to specify the elements in terms of which I am factoring. These are called irreducible, and they are elements that themselves do not factor further. Formally, P is called irreducible if any factor of it is either a unit or an associate of P. Notice that units are not considered irreducible, just like 1 and minus 1 are not considered prime integers. Okay, the word prime here has a different meaning. It abstracts a different property of prime integers. We say that an element is prime if whenever P divides AB, P divides A or B. In other words, the principal ideal generated by P is a prime ideal. And it is proper because I do not want units also to be prime elements. Okay, the relationship between the notions of prime and irreducible is important in characterizing UFDs, as we will see. Now I can define uniqueness of factorization as a product of irreducibles. First, I can change the order of these elements, and second, I can multiply by units. For example, in integers, 6 is 2 times 3 but also minus 2 times minus 3. If these two are the only ambiguities in factorization, then I say that the factorization is unique. And a domain is called a UFD if every non-zero non-unit has a factorization as a product of irreducibles and it is unique in this sense, which I have made precise over here. Okay. Now that I have this definition, I'd like to look for different characterizations. For that, I need to see when a factorization exists, and when it exists, how can I ensure that it is unique? So let's see that next. This theorem gives a characterization of unique factorization domains, and it is not hard to prove. So let's first do the forward direction. I assume that I have a UFD, and first I will show that every irreducible element is prime. So let's start with such an element P. I need to show that if P divides AB, then P divides A or P divides B. Because P divides AB, I can write AB in the form P times some element C. Now, by hypothesis, I can write down factorizations of C, A and B, and I get factorizations of the left hand side and the right hand side, which must be the same up to associates by uniqueness. But P occurs visibly as an irreducible element of the factorization of the left hand side. So it must occur on the right hand side also up to some associate, and therefore it must be part of A or part of B, and I am done. Okay, let's see what the second condition is saying. It talks about an increasing chain of principal ideals. I can assume that all of these are proper ideals because if the entire ring occurs somewhere, then I just stop there. Now, this strict containment of proper ideals means that B2 is a proper factor of B1. So, I have the following situation. I start with B1, B2 is a proper factor of that, B3 is a proper factor of B2, and so on. The condition is saying that this cannot go on indefinitely. So this is a finiteness condition. See if you can prove it. We already saw that each B is a proper factor of the previous B. Therefore, all of them are distinct factors of B1. Now, write down the unique factorization of B1 like this. And by the same logic as over here, we see that such an element can have at most 2 to the k distinct factors. All the B's are distinct factors of this element, and so there can be only finitely many Bi's, and I am done. Okay, now since we talked about distinct factors of a given element B, here is a useful remark. I can just write down all of these factors, and for doing this, it is useful to gather together all the equivalent irreducibles that come in the unique factorization of this given B. I have written down all of these distinct factors over here. This works just like for integers, and you should check this. Okay, now we should prove the converse, and this is more interesting, so see if you can do it. First, we will assume only condition 1 and prove uniqueness of factorization. This works exactly the way you did it for integers in the homework. So let's see. Suppose I am given two factorizations of the same element. Now, P1 is irreducible, so it is given to be prime, and it divides the product on the right hand side, so it divides one of the Q's. Let's say Q1 by reordering if necessary. Now, Q1 is also irreducible, and therefore it does not have any proper factors. So P1 has to equal Q1 up to multiplication by some unit. Now, cancel P1 and continue. Okay. Notice that the definition of prime was made in such a way that this argument works. Alright. Instead of saying continue, we could have done induction on the minimum of K and L. The base case of the induction is then just the definition of irreducibility. Sometimes the length of a factorization in a UFD can be a useful thing. For example, you can do induction on it as we did over here. Alright, now the only thing that is left is to show existence of factorization. For this, we will use only condition 2. This is the only place where some new reasoning is required, so see if you can do it. Let's remember that having a proper factor means having a larger principal ideal. Now, P being irreducible means it has no proper factors. So, there is no larger principal ideal than this one unless it is the entire ring. Now, I want to show existence of factorization from condition 2. So, take an element B and start extracting successive factors. That means I am taking an increasing chain of principal ideals and I go as far as I can until it terminates. That just means that at the end I have obtained an irreducible element, which is a factor of B. So I have a factor P1 of B. Now I write B as P1 B1. If B1 is a unit, then I am done. Otherwise, I do the same procedure with B1 and write B1 as P2 B2. So B is P1 times P2 times B2, and I can continue like this. But there is still a question, why does this procedure terminate? So take a moment and try to figure this out. This requires another application of condition 2. As I keep extracting successive irreducible factors, look at the B's that remain. Now, each successive B is a factor of the previous B. Therefore, the principal ideals generated by these B's give me an increasing chain. By condition 2, this has to terminate. When it is forced to terminate, I obtain an irreducible B, and so I have finally a factorization of B into product of irreducibles. Okay. Another remark, notice that in the backward direction, I separately proved existence of factorization from this condition and uniqueness from this condition. Could we have done this in the forward direction? You can think about this. We have seen two conditions. The first one ensuring existence of factorization and the second one ensuring uniqueness. So let's make some remarks about each one of them, starting with uniqueness. In this condition, I want every irreducible element to be prime. What about the converse? It is a fact that a prime element is always irreducible in any integral domain, regardless of unique factorization. This is simple to see. You just use the fact that if P is equal to AB, then certainly P divides AB, and now just use definitions. I have written the argument here, but you can really just do this on your own. Next, I have the very important observation that in a UFD, I always have GCDs. So let's remember the definition of GCD of A and B. It is an element that is a common factor of both A and B, and any other common factor of A and B should divide this one. So, using the definition and using the UFD property, try to prove this statement. If you thought of linear combinations, then that is not right. In a principal ideal domain, I know that GCDs exist and can be written as linear combinations. But PIDs are special kinds of UFDs, as we will see shortly. In a general UFD, GCDs need not be linear combinations. For example, we will see that the ring ZX is a UFD, but here it's easy to see that 2 and X are relatively prime, but their GCD 1 is not a linear combination of 2 and X. So in a UFD, to write GCDs, I should first write prime factorizations of A and B. Notice now I am saying prime factorization because I just saw that in a UFD there is no distinction between irreducibles and primes. Okay, once I write down the prime factorizations, I remember that I already know the list of all factors of such an element. So using this, you should be able to write down the GCD and you should also be able to write down the least common multiple, just like over integers. So please do that. Notice that I am allowing powers of these primes to be 0, interpreting p to the 0 to be 1. This allows me to have the same list of primes occurring in the prime factorizations of A and B. For the GCD, I take the same list of primes and raise each one to the smaller of the powers to which it occurs in the prime factorization of A and of B. Now, both requirements in the definition of GCD are met quite easily, as you should check. Next, I can use a similar idea to calculate the least common multiple. I take the same list of primes and raise each one to the larger of the powers to which it is raised in the prime factorization of A and of B. Observe as usual that the product of A and B is the product of their GCD and LCM. Alright, so we saw that in a UFD, GCDs exist. Conversely, it is true that if in an integral domain all GCDs exist, then that implies the second condition, that is, every irreducible element must be prime. You can do this as an exercise, it is not very difficult. Therefore, in the characterization of UFDs, I can replace the second condition by the existence of GCDs. In the last remark, let's see a very interesting example of a domain where this second condition fails and therefore it is not a UFD. I take this imaginary number alpha, square root of minus pi, and adjoin it to z to get this subring of complex numbers. Notice here that 6 can be written as 2 times 3, but also as 1 plus alpha times 1 minus alpha. Now, I claim that both of these are essentially different factorizations because all 4 elements are irreducible in the given ring and no two of them are associates. How do I prove something like this? I use the same tool as before when I found the units inside Gaussian integers. The norm of a complex number is obtained by multiplying it by its complex conjugate. I get this expression for this ring here, which is a strictly positive integer as soon as I start with something non-zero. See if you can use a standard property of the norm to prove these two claims. Norm is multiplicative, so an equation of this type in Z alpha gives me an equation like this in integers, and such an equation in turn imposes strong restrictions on factoring in Z alpha. For example, if 3 were to factor like this in Z alpha, then 9 would need to factor in this fashion over integers. And you check quickly that such a factoring is possible only in the trivial way. This shows that 3 is an irreducible element in Z alpha. And the same method proves both of these claims, giving me that these two factorizations are essentially different in Z alpha, and therefore all 4 of these elements are irreducible but not prime in Z alpha. Despite this failure, there is still nice factorization in Z adjoined with alpha, just not of numbers. Dedekind proved that every non-zero ideal in this ring can be written uniquely as a product up to reordering of prime ideals. Remember that we defined the product of two ideals and that was again an ideal. This result is closely related to unique factorization in a PID. In a PID, every ideal can be identified with a number up to units, but anyway for factoring we disregard units. In rings like this, not every ideal is principal, but still non-zero ideals can be written as products of prime ideals uniquely. Such a result is why Dedekind named ideals as ideals. Namely, they can be thought of as idealized numbers that repair this flaw in factorization. This result is true much more generally for rings of algebraic integers in algebraic number fields. This is a beautiful story in algebraic number theory, and you can get a taste of this in chapter 13 of Artin's textbook. In the last example, uniqueness of factorization failed because this condition was not true. But factorization into irreducibles still existed because as I keep factoring, norm keeps going down. So the question is, are there any rings where this condition fails and therefore factorization need not exist? The answer is yes, but not very often. This condition requires that all increasing sequences of principal ideals should terminate. In fact, for most commutative rings that are of interest, all increasing sequences of all ideals terminate. Such rings are called Noetherian rings. So, this condition does not really fail very often, but it does fail sometimes, and here are a couple of examples. Both are integral domains. The first one is the ring of all functions that are holomorphic over the entire complex plane. The second one sits inside the ring of rational polynomials, and we take only those polynomials that have integer constant term. Note that if I start factoring x in here, then I can take constants out as many times as I like. Okay, what is interesting about both of these examples is that the second condition is still true. Any two elements have a GCD. In fact, the GCD is a linear combination because every finitely generated ideal is principal. Such rings are called Bezier domains, and they are a generalization of principal ideal domains. But they need not have unique factorization property because the first condition might fail. So in these two examples, failure of factorization came purely from the failure of this first condition. Finally, as promised, let us show that a PID has unique factorization by showing these two conditions. The argument for the second one is already done in homework 0, so please do this now. Remember that in a PID I always have GCDs, and GCD of A and B can be written as their linear combination. Take an irreducible element P dividing AB but not dividing A. I need to show that P divides B. Because P is irreducible, its GCD with anything can only be 1 or P. But P does not divide A. So the GCD of P and A has to be 1, which is then a linear combination of P and A. Now I take this equation and multiply it by B to get this one. The first term on the right hand side is divisible by P and the second one is 2 because of this condition. So B is divisible by P and I am done. This kind of argument should now be routine. Okay, now suppose I am given an increasing chain of principal ideals and I need to show that it terminates. Here a small new idea is needed. In general, union of ideals is not an ideal because it may not be closed under addition. But union of an increasing chain of ideals is an ideal. You should check this and see if you can complete the proof. So, the union of this chain of ideals is an ideal, but every ideal is principal, so this union must be generated by some B. But then B must be contained in one of these ideals. Suppose it is contained in A and R. Now, B generates all of this union, but B cannot generate anything outside this ideal. So the chain has to stop here. Okay. Finally, it is worth remembering that PIDs are very nice rings. I really like Z and Fx, and there are other examples. But the class of UFDs is much larger. For example, we will see that these rings are UFDs, but you can check that they are not PIDs. There are many more examples.